ist Computer Doktor, everybody does get flat. Computer ist Computer Doktor, you put it all on, put it all on. Computer ist Computer Doktor, everybody does get flat. Computer ist Computer Doktor, you put it all on, put it all on. Computer ist Computer Doktor, everybody.
Hello, fellow humans, cyborgs, robots, and extraterrestrials. It is I, your friend, Deadprogram, and of course, my wonderful companion, Gopherbot, coming to you live from La Pipa in Asturias, España. And we are here today to talk about all sorts of fun things in the worlds of technology, life, the universe, and everything else. I believe that is all inclusive. All right, so let's go to the news. First of all, the biggest news is I have had my first vaccine dose. I may have told you that last week. So just a few more weeks and I will be ready to go out in a mask still. But it's all right. Anyway, let's talk about what's going on in the world of technology. This week has actually been pretty awesome. My friends over at Google have been very, very busy, and they've created a really cool new project called Open Source Insights. So Open Source Insights is sort of a advanced version of a project done by called libraries.io, which was designed to basically track the dependencies, track all the dependencies of any given software project that you're using, so you could track things like licensing issues or security problems. So they've been working on this project for a while, and now the story can be told. It lets you take, and it supports several different package managers. So here we can play with it for a real quick second. Open Source Insights at deps.dev. So it supports packages from NPM if you're using Node, Go modules if you're using the awesome language Go, a couple of other package, Cargo if you're a Rustacean. So I was playing with this before, and we can enter in a package. For example, we can enter in GoCV, and yes, it pops up here on the list. And so it comes up with information about the GoCV package. For example, what dependencies it has, which it has very few external dependencies other than OpenCV itself. So we can take a look, and it is very small, shows that we're using Go from Pascal Declo, and also the MJPEG package, and those are actually used in the testing and one of the demos, respectively. So if we clicked on that package, then we could go and take a look and see its dependencies. And we can also see who depends on GoCV. So it turns out there are a lot of packages that are using GoCV in order to get their work done. So many, apparently, that due to the large number of dependents, we only show a sample in the list below. And I was looking at some of these, I'm like, invisibility cloak. What is that? That looks interesting. So this person apparently used GoCV to make an invisibility cloak, and only dependency was GoCV. So very powerful stuff, very cool. Check it out at deps.dev. So also from our friends at Google on the Go team, this week they have finally merged into the dev branch the new fuzzing capability. Ooh, little fuzzy. What is that? Like, I'm fuzzy, but what about you? All right. What is fuzzing? So fuzzing is actually when you're testing software and you start just putting junk, trying things that shouldn't work, garbage keyboard input, plugging and unplugging cables, just generally doing things you shouldn't do with the intention, of course, of causing the software to break, and as a result, possibly using that to exploit for unsavory purposes. You don't want that. So turns out that it's one of the things that we can try to test for is by doing, random crazy variations during test. We can find problems before they occur. And so this is actually getting merged into Go as part of the normal test routines, that you'll be able to use this as part of an additional testing capability, the same way as we are able to do benchmarks and profiling as part of our tests. So very cool stuff coming from the team. So in the world of other awesome software, our friends over at JetBrains, a very cool company, been using their tools for many, many years. So GoLand is a not open source editor. It's a product, commercial product, but it has a lot of capabilities to plug into it. So they got a couple of their interns to work on, and they now have recently released a TinyGo plugin for GoLand. So I wanted to show this to you, but I couldn't find my license key for GoLand. That was kind of embarrassing. Hopefully I'll find it next week and I can actually show you some of this. But you can install this plugin and it gives you one of the main features that people have been clamoring for, which is auto completion and auto imports for things like the machine package. So it'll just pop right up with the list of your different pins and LEDs and all these mysterious options that some of which are kind of hard to remember. So very cool stuff coming from our friends over at JetBrains. And then speaking of friends over at other companies, next Thursday to be precise, at 1:30 p.m. Eastern Time, and that would be 7:30 p.m. Central European Time, I am going to do an interview on the Hello World program put out by Microsoft. Thanks to my friend Aaron, who is a developer evangelist over there, Go fanatic, and generally awesome human being. I will be doing an interview to talk about TinyGo. So it's going to be really fun. I'm looking forward to it greatly. Really cool program. Actually, I meant to mention this in a previous show, but it turns out they did a whole show about Go CV back in April, and I didn't even know. That was how awesome is that? So definitely we'll check that out. And then, so let's take the mask and put that back on because I think it's time to bring my friend Lorenzo out. So we were working last week on making a bunch of changes to, wrong camera. There we go.
Hello, Ron.
Hey, how you doing?
I'm fine, thank you.
All right. So last week we made some progress. We found a few problems, and I saw that you reported the issue with flashing on Windows, and I saw there was a little bit of communication. Hopefully we can test that out today.
Yes, we can have a look. Let me bring my stuff here, and we can.
So what we're doing, if you haven't seen all the previous episodes, is we are working on going through the GopherCon. Where is it? There we go. We're going through the workshop content that was used at GopherCon 2019, which was one of the last live events, and using the Arduino Nano 33 IoT board, which is a cool microcontroller with a built-in Wi-Fi chip. There was a series of activities to learn how to program in TinyGo. So we've been going through each of the different steps, and we got to, I think, step 5. Step 4, I guess. Which one did we do last time?
Step 4.
Step 4.
Yeah, we are on step 5.
Okay, great. We're on step 5. So let's jump over to the table view here so we can see. This is the board.
Yes, let me clean up this mess a little bit because I think some cable might have come out, but we have a look. Let's see if it works.
So this is the microcontroller itself. This on.
Oops.
Oh, something's working. That was the program from last week when you pressed the touch sensor. It was
Exactly, and also the two LED switching on and off alternatively while pressing the button.
It's actually working. Amazing.
Yeah, still works.
That's a good sign.
Absolutely.
That's a good sign. So I know last week we kind of were getting sick of the same problem, which was, here we'll jump over to your computer.
Yes.
That when you were trying to use the TinyGo flash command, that it was giving this kind of nasty error message about some extra parameter.
Yes, we can run it again to see what happens. And let's see. If we
So I did notice that the
can, oops.
so the suggested solution was to change the location of your temporary directory
Ah, okay.
because
That's
the
also right.
problem apparently has to do with your name is a first name and a last name
With
with a space.
Yeah,
And
they-
apparently that was something we did not take into account when we were working on this, was that there could be a space in a directory name. And actually, there is a draft pull request to fix that problem completely, but as a shorter term solution. So I see you created a TinyGo temp directory.
Yes, but I think we need to install something over here, I guess.
I think what you need to do is you need to use a set command.
Okay.
And if we go to the TinyGo repository on GitHub,
Yes, I'll have it here.
then we can maybe take a look at Takasago-san's comment of how to try to fix this.
Oh,
So what he was suggesting in this was to use the set command to set the TMP environmental variable in Windows to this other directory so that it would
oops. Sorry.
hopefully, so that should work,
Yeah.
hopefully. So I guess we'll be able to find out if we can just do a flash normally without having to
Let's change.
to
it.
first build it and then separately flash it with the BOSAC command.
Let's say step 5 directly, right?
Well, step 4 was the last one you had working, right?
Oh, yes.
So let's just try to reflash step 4.
Okay. Good idea. I think we need to.
Oh, you need to change directories to the directory with the code.
Okay, you're right. Let me. From here, I think it's users. Lorenzo.
So the auto-completion knows because it escapes it with quotes.
Yeah,
But
But
TinyGo was
that-
not so clever.
you had to include it. Tiny, I think it's TinyGo. Yeah. And Gopher.
And then it would be in the sensors Arduino subdirectory.
Okay. Perfect. Here we are.
Okay. So yeah, if you up arrow endlessly,
And
hopefully this will work. Let's find out.
Ob is building something. A dot.
It worked!
Yep.
Yes!
Fantastic.
You had the -X and that's why it gave you the verbose version.
Okay.
So is it actually running though, is the question.
Yeah, still.
Amazing!
Do we need to reset it? But I think if it flashed it, we are safe.
No, we don't have to do that anymore.
Okay.
See, that whole process of double tapping and going to the other BOSAC program, that was something we had worked on quite extensively to make it better for Windows users. So when you first ran into that problem, I was very unpleasantly surprised because we had spent a lot of time and I had actually worked in workshops where people with Windows were using it. So it didn't occur to me that it would be something as simple as the directory naming. I was looking for some complicated technical reason why it would stop working.
Okay.
And of course, it was much simpler than that. Anyway, though, we have a fix that is going to hopefully merge for the next release of TinyGo, which will basically automatically escape directories and paths on Windows so that you don't have to do anything about this. It should just work out of the box.
Brilliant.
I guess when the next release comes out, hopefully in the next week or so, we don't have an exact date, but hopefully we'll be able to.
So I will request to close the.
Well,
the
the way we work is what we normally do is when we have an issue that we have entered, if that issue is not something specific to the current release only, in other words, it's like a problem that's been around for a while, then what we do is we would take and we would, instead of just closing it, because other people may have the same problem before the new release comes out.
Okay.
Instead, we just label it that it's next release, and that way, when the next release comes out, then we can close it.
Okay.
That's why if you take a look at our releases, you'll see whenever we have a release, we have a whole bunch of issues that get closed because I go and I use that label to find them all and close them. I could write a script, but it's very satisfying to click on them.
Okay.
So hopefully we'll be able to fix that problem. So I did notice that there were a few of the other programs that also needed to be updated. So if you were to go and do a git pull, you may want to change directories to the root. I'm not sure if that matters.
I don't know either. So to TinyGo, right?
Yeah, well, just the root of the GopherCon 2019 directory. So that'll do it.
That's one.
So you need to get the latest updates that I pushed to the repository late last night. So if you do a git pull -- rebase, so it doesn't add a merge commit, space origin, space master, one of my almost favorite commands, and then hit enter, it should pull down all of the latest changes. So now we should be able to compile steps 5 and beyond because I've made some changes. So if you want to go and bring up the web page with the instructions for the GopherCon 2019 website on GitHub.
Yeah. On Git, yeah.
Probably I will rename this repo when we're done going through all the rest of them to something a little more generic.
Okay.
Because this isn't just about GopherCon 2019 anymore. This is about the whole universe.
Oops. Answers Arduino. Here we are.
Exactly.
Step. We go.
So we were on step 5.
Mm-hmm. I cannot see very well with my fog on the lenses. Okay. Step 5. Here we are.
Yes, you need a trapo.
So we are going to add basically a dial, a potentiometer, to the current installation. Actually, I did it because it's very similar to all the other, except so power, positive and negative, still the same in the two power supply binaries in the sockets, and the signal this time goes to an analog pin, which is A0, and it's located, it's on the lower leftmost and 1, 2, 3, 4th pin, A0, and it's connected. I guess I cannot see it very well here, but I think it's down there. Can you? Yeah, it's the 4th, right? Is this yellow one?
1, 2, 3, 4. Yes, it looks like
Yeah.
the 4th.
Perfect. We can. So it's.
It happens to be the 4th.
Yeah.
Oh wait, was it the date or the pin number? Just so happens in all of the craziness, I forgot myself. Push the button, see what happens. Okay.
So
So do you want to bring up the code?
Yes. From the repo directly, and then we flash it. Okay.
Mm-hmm.
Step 5
Step 5.
and main. Oops. And here we have it.
So it's a little small. Maybe we can. Maybe you
right.
can.
Let me see.
I just hit. What is it? Shift
Yeah.
Control plus.
Okay,
Oh, well,
yeah.
you're way ahead of me, man. You're way ahead of me.
Okay. So here we have it.
All right. So it's basically, as you've already noticed, like all the other programs, we just take the code we have usually and we just keep adding to it. We might do a little refactoring as we go, but generally it's just keeps adding capabilities until at the end it's the full system, doing all of its things. So we start out with a package main, same as
Yes.
before. We're importing the machine package from TinyGo with the hardware abstraction layer, and then the time package, which is just the normal Go standard library time, and then the TinyGo drivers buzzer, which is the driver that knows how to control, a really simple speaker to make it bleep and blop, not play full music. We'll get to that in the future driver. And then we've got,
This is new.
now we've got something new. So we can declare variables in Go a couple of different ways. One is if we use a var section, short for variable, and you could say var in a function itself. You could say var and then the name of it. That's what happens when you say colon equals.
Okay.
Colon equals declares it and assigns it in a single operation. And we don't have to usually specify what is the type, because Go is a compiler, a strongly typed compiler, and so it uses type inference to look at the right-hand side and say, what is this? Because I don't need to have a var and then declare the type if I can guess what type it is. But in this case, so we have var, and then the first one we say is PWM, which is our pulse width modulation, which for those who don't know what PWM means, PWM, pulse width modulation, is a way of turning a signal on and off very quickly in order to make it seem like it's an analog signal from a digital one. So if we want to only be a light, turn a light on, but only half the strength, like a dimmer, if we have it on half the time and off half of the time, then it will appear to only be at half of the strength. So we can use this to control the brightness of LEDs or the speed of motors, different sorts of things. So it's very useful capability, hence PWM. And so in this program, we're saying that the PWM is equal to machine.tcc0. So what does that mean? So the machine package is our hardware abstraction layer. So it says this microcontroller has all these different capabilities. And so TCC0 is one of the timers. So on a microcontroller, you can have something that happens automatically at some periodic interval. Like if we wanted to have something happen very quickly, like the oscillation of a speaker to turn it on and off very quickly, like we could use this timer to do that. And so TinyGo's pulse width modulation feature uses timers in order to turn things on and off very quickly, because that's what they're very good at. So we have to specify which timer to use, since many chips have more than one timer. And we can use them to control many things all at the same time, many different LEDs or many different motors or servos. So first we declare which pulse width modulation timer. Oh, fell asleep. I talked too long. That's how you know. So then this next line, it says green is equal to machine.t3, or D3, sorry. So that's just the pin.
The digital pin. Yeah.
Exactly, the digital pin. Number 3 that the green LED is plugged into. And then last we say channel A is an unsigned integer of size 8. Mm-hmm. So it's just a single byte. So channels are what a pulse width modulation interface can have more than one channel. That means we can use a single timer to control multiple servos if we want to.
Interesting.
And so in this case, we're just going to control a single channel, which is going to be the green LED. So let's keep scrolling down so we can see the rest of the program. So now we say machine.init ADC, which is telling TinyGo to initialize all of the analog to digital converters.
Okay.
And then we have a line that says init PWM, but that's not the machine package. That's just a separate function. That's because instead of adding all the whatever 8 lines of code to initialize the PWM right here. Instead, let's just call a function so that we can separate that from the rest of the code.
Okay.
So if we scroll down a little bit,
We go to init. It's a func.
it's a func.
Yeah, here we have it.
Exactly.
Oops, sorry.
So let's see what it does. So the first thing it does is it calls pwm.configure, and it's passing it a machine.pwmconfig structure, but with nothing in it. So it's just the default structure.
Okay.
So this is saying we're going to try to configure the PWM, and we're going to return an error. And then the next line, we're going to say if that error
If there is an error,
is
then-
not equal to nil, in Go, an error is actually a type. And so if we return nil type, we can check that and say if it's not equal to nil, that means there was some error actually returned. Then we're going to print a message that we failed to configure the PWM and return.
Okay.
Okay?
And if it's all good,
Then we continue on.
okay, channel A, R again. So this time PWM channel and green. What was green? I think we configured above.
Yeah, so now this is using a capability of Go, which is very similar to Python. It's that we can have multiple assignment,
Yes.
that we're going to assign to the two variables, channel A and air, what's returned by the function pwm.channel, because that returns two values.
Okay.
And similar to Python, the first value returned will be in the leftmost
Yes.
variable and so on. So it keeps
Okay.
them in order. And then we're going to say pwm.channel is how we'd say this PWM, we need to obtain a new channel for this particular pin, the green pin. So we're saying this PWM is going to control this green pin with a new channel, and it returns the channel number,
Okay.
which we're putting into channel A.
Okay.
So if we had multiple LEDs that we wanted to control separately, we would just call pwm.channel for each of them and declare a channel A, channel B, channel C, for however many things we wanted to control.
Okay. Yes, I forgot the green was associated to the digital connected to the LED.
Exactly, to the pin. So it's like a one, I should have a diagram of this, I'll make one.
Okay.
One PWM can control multiple pins.
Yeah, here we have it. So
Exactly.
okay, so you can configure as much as you wish on that.
Well, as many as can be
Okay,
supported by
support,
the
yeah.
timer on the chip you're trying to use.
Okay.
So that initializes the PWM, and now we're ready to go. So then we have the same code as what we had in the previous step. We declare the blue LED on pin D12, configure it as an output.
Okay.
The button on pin D11 as an input. The touch sensor,
Yes, this everything was configured as
exactly,
same as the last
exactly
time.
the same. The buzzer,
Buzzer,
same.
And the difference is here, I guess, where we are going to configure the dial.
Exactly.
So it's machine A0.
Exactly.
And it's calling the ADC analog to digital converter machine library.
Exactly.
So
So it's the same pattern you see that we're configuring the ADC pin the same as way we're configuring, the normal GPIO pins. We always have a configure method, and then we pass it some type of config struct. In this case, it's just the empty struct because it's the default values, whatever
the
they are.
default. Okay. So now enter the loop,
Exactly, entering the loop.
and we are probably reading the value of the dial.
Exactly. So we get the value of the dial.
So dial machine ADC get will read the value of what's connected onto the analog pin.
Exactly.
PWM set. I think here we are actually configuring the PWM to return a PWM value from what's our channel A.
So this is actually setting channel A equal to this value. So if we wanted to turn on the pen at some particular duty, which,
Like
if we
a
remember, our
frequency.
duty cycle is how much of the time is it on versus how much it's off. So we want to set a duty cycle. And what duty cycle are we setting? So we have PWM top is what's the top speed in terms of oscillations? You know, how many cycles per second can this PWM pin support? What's the maximum?
That depends on the Arduino in our case.
Exactly. That will be different for different pins or different PWMs and timers. So we have to have a way to return that so it's always generic. And then we're going to multiply that times the dial value, which is how much it's turned from 0 to FFFF, which is the highest value for an analog to digital converter returned. And we're going to divide that by the max value. So in other words, if it's turned all the way down, we're going to multiply the top times 0, which will be equal to 0, so it turns it all the way off. And if we turn it all the way up to max,
It will return.
it's going to return the highest value, which is hex FFFF,
Okay.
divided by hex FFFF, no, 4Fs, is 1. So the top times 1 is the max value. So if we turn it all the way up, it'll be at the highest possible value. And if we turn it all the way down, so this is just a way for us in one line to scale that value based on the actual top that this particular PWM supports.
Okay.
That way, if we're on a faster chip, that could be a higher value, but it'll still do what you expect, which is when you turn it all the way down, it's at 0%, and turn it all the way up, it's 100%. And then from there, it's the same code as before.
Yeah, switch on and off, depending on buzzer, time sleep. Okay. So I think we
That's
can
it.
go
So-
and flash.
So let's see what happens.
Let me see if I can get the. I have to move on to the sensor,
Exactly.
Arduino, and I guess we can do step 5.
Yeah, that should work.
If we,
We'll find out.
Good. We have the object. Whatever.
It's flashing.
Oh,
All right. Something happened.
But nothing. Because probably we have it at minimum. Let's see if it's.
Do we have the other LED plugged in?
Yes, it was working before, but not now.
I only see 2 LEDs. Did we only use 2? I thought we had a third one.
No, it's 2, if I'm not wrong. Step 5 was just.
Maybe we're controlling the green LED. That's right.
Yeah, we're controlling the green one, but probably we have to push the button, and we try to. Here we have the. Try with the button, push it.
I don't think that should
And
matter.
No, okay, nothing. Probably. Let's see if the connections are still good. Or otherwise, we can switch to step 4 to see if it's a connectivity problem with this LED. Because it was working before, eh? We didn't touch it. Yeah, everything looks... So this time,
So do we have it plugged in?
maybe it's on the wrong...
It looks like
The pins are the same as the previous step, I guess.
Yeah,
So
they should be. And then it is a rotary angle sensor, not a. No, that's good.
okay.
No, I didn't. There's not a rotary encoder in there because that would be very confusing to people. That looks the same, but it operates completely differently.
So the thing is, because this is like we have a 0 value, and probably it's not getting the power.
So one thing we can do is we could put in some logging code to our serial port and see if anything's coming out.
How?
Right? So if we go back to our program,
Okay. Well, we need to. No. Okay, we need to edit the.
we'll have to edit the program in.
This time I know the command, so it's not. No, I have to get into the directory. CD step 5, I guess, and notepad step. No, sorry.
I think it's Notepad main.
Yeah, that's the thing. Notepad main. Okay.
All right. So if we go down to our part of the code where we are setting that value, right after that we could say print line,
Before or after?
like after the PWM. And so, in other words, not inside the if. So,
Sorry.
right after the
Okay.
PWM value,
Sorry.
if we say print line, print ln, and then we just say dial value.
It's like this, no?
No,
Sorry.
let's just print the value. We don't need to print.
Okay, okay. The value is dial. Sorry, you're right.
Yeah, no worries. Dial value, and then close paren. Hit an enter just so we have an extra line to find this later.
Okay.
And that's it. So you should be able to save the file.
I think it's saved. Well.
And then we should be able to compile it again. Exactly. I guess we'll find out. Now, if you want to get rid of the -x, that way it's not quite so verbose. Because now that we know it's actually working, it'll still give us output, but just not the whole command. Okay. So now we have to open up a terminal. So you can use PuTTY, or you can use the Arduino terminal.
Oh, I don't have either of.
You have to have some mechanism for opening a serial terminal. So yeah, PuTTY's a good one.
Let's download it then, because I don't have it installed. Shame.
Oh well, you're going to
No,
need
no,
it
no,
for
no.
this. So let's download it real quick.
But I don't. Sorry, I need it in English.
Yeah, no worries. I don't know if that's the. Where's the legit place to download it?
You're right.
I don't know.
Well, I think Softonic is. Let me see.
I'm not sure.
I think it's this one, if I'm not wrong.
I don't actually know. I'm very suspicious about downloading things from random sites.
You are right. But for Windows operating system, I think.
I'm surprised that Windows still doesn't have a terminal program built
I
in.
don't remember, to be honest. It's a while I'm not using SSH something, no?
Wait, there's a new Windows terminal. Microsoft Terminal. Is it do serial? Hold on. Let me make sure that it's serial. Port. Let me just make sure it does what you think. Yep, Windows Terminal.
Okay. So
It can't have a worse UI than PuTTY. Yep, this is it.
it's the same as the one we. But from here it's like.
Well, no, you don't want PowerShell. You're in PowerShell. That's not what you wanted.
Okay. And then, so it's CMD.
There's an application called Terminal. Windows Terminal, I mean. So if you type Windows Terminal.
It's this one. Let me see. Probably it's redirecting us to PowerShell.
Well, I don't know the answer.
Let me see how it looks like.
Let's see. It looks like you can say.
Can you go? It's Minicom.
Oh,
It's from the terminal. Probably you have to run Minicom. Let's see. No.
you have to install it first.
Okay.
So you can get it on your WSL1 distro, apparently, if you type the following commands. WSL.
Okay. Let me download it then. Sorry again.
I don't know if this is going to work. But
Sorry. What's?
so it'd be WSL space -D for download, I guess, space Kali -Linux,
No.
KALI -Linux, space Minicom. I've never tried this.
No.
Nope. Okay, so no. All right, so much for Scott Hanselman's instructions. We probably skipped several blog posts worth of instructions before that. Okay.
Let me.
Well, back to where,
You
let's
don't
see.
want a serial connection to the...
Yeah, we just need to see the serial output so we can see what values are coming back from the analog to see if it's even working. So let's see. So real
No, we have to
putty
put-
download. Stack Exchange. Which reputable site should I download putty from? The official site is that chiarkgreenend.org.uk. In other words, not that first one, not that second one. No, keep going. I swear it's going to be in here somewhere. That one, yeah.
One. Ah, okay,
Like
okay.
fifth down on the list is the legit one. Don't be scared.
MSI, that's the one. I guess I can go for this one.
Yes, exactly. 64-bit,
Yeah.
x86.
Oops. I did it.
It's okay, you got it twice.
Open.
Yeah, this is a good program to have.
Yeah, usually I used to hide it, but
It's not the best user interface. I mean, at least I found it somewhat confusing. But I think if you use Windows keyboard shortcuts more frequently, that might have a lot to do with it. Okay. So, I think it was COM, I don't know which COM. So
maybe
serial,
well, we can have a look.
I think it's COM 13.
We changed the last time, remember? So we'll have a look now and that's what I did. Manage device manager. Ports and comms. 810.
COM 10. Okay, so go back to
So,
PuTTY.
Let's go back here.
Say COM 10, and then your speed should be
11.
no, it's 115200.
Okay. 5200.
115.
115. Sorry, I forgot about those speeds.
Yeah, I know, high speed. Okay, so now you should be able to say open.
Oh yes.
And yes,
it's beautiful.
and so some data's coming. So
let's see if we turn this one, we should see now the reading. It does.
Yeah. Okay.
Maximum value, and so yeah, it's working. But
Okay.
the LED somehow.
Well, there must be an error in my code for setting the PWM. So I guess we can exit PuTTY. Now that we know that that's working.
Okay.
How do you do that? I don't know.
I have no idea. No, it's okay.
Okay, excellent. So let's go back to the code.
Sorry. Ui. Oh, horrible, because I might have some password over there.
Uh-oh, well, nobody saw it. Okay. So now if you bring up the program again, let's take a look and see if there's...
Sorry, yes.
I must have done something wrong with the... when I was playing around. I didn't actually have a chance to test it. That might have been helpful.
Was it? I forgot completely. DIR. I am doing something wrong. Sorry, CD sensor. Arduino. And okay, it's a directory. It's not a program. It's step 5 and notepad main. Go. Here we have it.
So actually, one idea would be let's output the result of the calculation
And
instead of outputting dial value.
yes,
Let's copy the whole PWM top, the whole
yeah.
calculation, and then let's display that. That way we can see, whatever it is we think. Do we have the right number of parens? It looks like it. Okay, looks
let's
good.
try.
This way we can maybe take a look and see.
Oh, oui. Sorry. Yeah.
No,
I'm sorry.
no worries.
It's sensor.
Arduino.
Arduino.
Exactly.
And again, 1, 2, go.
There we go.
There we go.
Let's see what happens. This way we can sort of see. I know you're supposed to use real debuggers,
And let's
but
connect
you know,
again.
Printline is the debugger of champions. It's the first debugger, the pure debugger. It's the primordial debugger.
Yeah. Yes, I think it's.
Actually, I guess the primordial debugger is a single LED flashing. So I guess this is the first debugger to walk erect on 2 feet, perhaps, if we're going for metaphors.
Oh, yeah, we flashed it and see how it behaves. Let's see the maximum value.
Yeah, and the minimum value. It certainly looks like what one would expect.
65.55, so it's FFF. No, I guess.
Yeah, I mean it jitters around a bit just because analog
Yeah.
ADCs tend to do that.
Yeah, usually.
That's where hysteresis is so important. You know, averaging the numbers so you don't.
Yeah.
I found that that's very useful when
Properly-
flying drones using analog control sticks.
And properly grounding, pulling up, pulling down, etc.
Exactly.
Kind of.
And there's also settings you can use if you want to use a separate analog reference voltage instead of just the power that's coming over the USB. But in any case, it certainly seems like it should have been working, but it's obviously not. So I guess we should, and we saw it working moments ago when it was plugged in for the other program, right? Because we saw it.
We can reassemble the entire circuit if you like. I can do
don't-
it for the next
I
exercise.
don't think so. I don't think so. I think we just have some small thing wrong. So I guess we can close putty
Okay.
because we are getting the channel back. Yes. And we are trying to set it to what we should be the correct value, which would be the top times.
Sorry, a notepad.
Oh, thank you. So you know we're setting channel A equal to that value, which would so what is channel A? It is we assigned it in our init PWM, right? If we scroll down a little bit to just
Sorry.
take a look at that. And we assigned the channel, and we said that it was the pen for, yeah, that should have been right, green, which is which pen?
Let's go.
D3.
I think it was this, as usual. We can count.
Let's take a look at the map.
Yeah. Where is it now?
I have a feeling it's in the wrong pen, the wrong place.
Green.
It's very easy to have that happen. If you go to the top where the
Yeah.
little diagram is,
Okay.
there we go.
It's this.
Oh, yeah, I think it's on the other side of the board up here.
Now that's. What was the number of the green pin?
D3. Wait, what?
Ah,
It's very easy to do this when everything's on the opposite side of the board.
mm.
Oh, yeah, go ahead. I don't want to take
No,
I don't want
okay.
to take the fun away from you.
No. Here, let me find out. So it's the third pin from the upper left. So it's
No, from the
it should-
upper right.
no, because here we are.
It should be.
Yeah, but we can change maybe in the code rather than unplugging.
I think that's a great idea.
No, but without flashing, probably you are right. If it's 3, then we move it on 3. Sorry, it's. But it's difficult to count. That's the only problem.
Well, let's make sure we don't unplug the wrong pin.
Yeah, yes, let's
So
do
I'll
it again.
wiggle it. It's this one?
No, this is the green. Hold it.
I know, but we had to plug. Oh, I got it.
The green, no?
I think, let's go back to the code. That may have been my mistake. So we're saying that we
Yes.
want,
Yeah, that's the wrong one.
I think that would be, D3 is a really stupid place to put that because where was the green pin in the previous example?
We can have a look, but I think it's 10.
I think that's where we should have left it.
Okay, let's go on.
I think that was my error.
3. and I think connect on D10.
Yes.
So
Okay, so let's go fix the
change
code.
and-
Yes, because that was an error on my part. I did not mean for that to be necessary.
and we'll flash it again.
Yes,
Flash dance today.
exactly. With a feeling.
Exactly. Okay. Yeah, at the end it's easier to leave it as it is and reflash. And but okay, now we can. Yeah,
It works. We forgot to turn up the volume.
Let's see. No, it doesn't affect anything else, right? The beep and so only the LED. Yeah.
So we can look at it on the
Yeah. Let's prove it.
Mesa.
As you can, it's very dim light, eh?
It's very dim.
That's very dim.
We're using most of the power available already. Can we even see it?
I don't know, but
I don't think you can see it.
no, it's over.
But it's definitely working.
It's working. Please trust us.
Yeah, trust us. We're technologists. It's not like we're doctors.
Okay.
All right. Well,
Fantastic.
so I got to fix that in the. I almost got it fixed last night, but apparently 10 turned into 3, missing 7, no good. But we fixed. What did we get done? We've proven that the temporary file location makes it possible to just use the normal flash command. Hopefully we'll get that pull request merged and we can actually test the full updated version in the development build next week. And we found an error in the step 5 with the pin, but otherwise it works exactly as expected. So, and we've got now which interfaces? We've got the GPIO in, we have GPIO out, we have analog in, and we have pulse width modulation out. We have 4 different styles of interface from this one chip so far. And then next we'll add I2C next week. We'll actually get this display to do something. The I2C. So yeah.
See, I see you made the driver as well for the font.
Yes, that's right. Otherwise, if you can't see
great.
the words,
Yeah, beautiful.
it has to say, bienvenido or something.
This
at
would
least.
be a nice topic to develop the nice fonts for the.
There's actually a surprising number of fonts, and since we're talking about it, so the font capabilities in TinyGo are largely the result of Conejo Ninja, Daniel Esteban, my good friend and awesome human being, resident and Spanish human being living with his family down in the south where it's very hot. I haven't gotten to see him in real life for quite some time, but he's a tremendous human being and an amazing collaborator and contributor. So he started on this tiny font project, basically taking a page from the Adafruit style of drawing the fonts as vectors, and it's not too slow at all. It works surprisingly well. So subsequent to that, other people jumped in, and so Sago35, our erstwhile Japanese contributor, they went and they created a command called Tiny Font Gen. So Tiny Font Gen will take it so you can import, I believe, any TrueType file, is it? Yeah. You can take any TrueType file and you can compile it to the Go code that we used for Tiny Font. So if you have a custom font, you can import that and you can use that. We just have some specific ones that we include, but there's a whole bunch of other ones that you could use. My personal favorite of all the fonts is the one that was contributed by Yana Rakil. So she currently works at Amazon, was formerly a member of the Go team at Google. Amazing person, a real genius, and also very creative artist and a very nice singer, musician. But she decided that we really need a font. Well, actually, she decided we needed a font in the world that is all gophers, right? Like gophers in different positions. You could do a dancing gopher. And then when Conejo Ninja saw this, he said, we need this as a tiny font because we need this on a badge. And I actually got the great pleasure to give her a Tiny Go badge, which is one of the, I didn't bring it with me today, but it's actually a wearable smart badge.
Oh, yeah.
And it had the font on there. So boy, was she stoked. It was great. She was so,
Super
it was
nice.
so nice to make another person who's done so much for the community so happy just with like a few bits moving around. It was awesome.
Fantastic.
But we'll see that next week. We'll play with that.
Okay.
Cool, man.
Thank you
Well,
very much.
thank you very
Ronnie.
much for coming. I really appreciate it.
A pleasure. I will-
Like a lot of stuff happening here.
Yes.
So exciting. I know. Soon we're going to be seeing fonts, and soon we're going to be done with all the steps, and you'll be ready to fly free, little bird, out into the world. And
Hopefully soon.
Hopefully
Thank
some-
you very much.
hopefully some of the bugs you reported will be fixed by then.
Yeah. Ciao, Ron.
Cool.
Thank
Ciao.
you.
Friend Ugo is here as well with us. So he's also an embedded programmer that I'm trying to pull into the world of TinyGo. Right now he's really involved in Python, but that's a temporary condition. No, but I love Python. I think Python's amazing,
Yeah.
actually. But I like Go too. Anyway, I don't know if Manuel is here.
Let me.
I don't think he made it back. I was going to try to do a demo. Apparently, we were going to try to do a demo of our machine learning system for cow identification, but I don't think he was successful. He was trying I'm going to get this demo working right before the stream. Famous last words. I say stuff like that a lot. I'm going to get it working right before the stream. All right, well, if he shows up, cool. If not, let's jump into some other cool stuff that we've got. All right. That was really fun. I'm really excited to get this tutorial stuff. Oh, no worries. All right. So, where were we? Oh, yes. So, a lot of really cool stuff has been happening in the world of TinyGo. Excuse me. And one of the things I wanted to show, I think 2 weeks ago, actually, maybe it was last week, time flies, was a pull request that was created by Sago35 for adding support for the FAT file system and for SD cards. So I've been really excited about this. Let me pull out. It was really hard, okay? It was not, like you use SD cards probably, and you don't think much about them. You just use them. They just work. You never think about, like, how does it work? Why does it work? What does it take? How many authors of drivers? So we have this PyPortal, which is a very cool board from Adafruit, awesome company from New York, who does a lot of great things with hardware and software. So this is one of the boards that they make that happens to have an SD card reader, and I happen to have this SD card. So if I go over to my Linux machine, and we'll plug in, hitting the buttons, it's thinking a little too hard. So if I go over to my Linux machine here, and let's go down to take a look at my terminal. So if I take the SD card and I just plug it in to my SD card reader that my awesome Dell XPS 13 Developer Edition happens to have, then it mounts that volume, and we can see that actually here is that drive, and it's got two files on it. It's got a go.mod file that's got in it, oh, it thinks that's a different file type. I should have said open with other application, and let's open it with, something nice and simple, like any old text editor will do. Actually, it'd be easier to just do this with a terminal. Here we go. So I can just say cat, and then I believe it's under media, run, and that's probably the name of it. Yep, go.mod. And you can see here, this is what's on that SD card, which doesn't have a nicer name than BE21-32F1, apparently. But that's what's in that one file. We can just do an LS for listing, just so we can see everything that's on there. Okay, 2 files on there, very good. So now I'm going to go and eject it. And that way I can take it out without damaging any of the data that's on there, which is in the FAT file system, which is the original file allocation table system used by MS-DOS, apparently, back in the day. And somehow has still managed to be around to be used by other people. It's sort of the most common, like when you go and you stick in an SD card and it says, do you want to format it so it can be used by any computer? It's FAT32 that's being used. So let's go and plug this in to the device, and then we'll go back over to Linux here. So there's a few different components that are in use in order to make this all work. Okay, one is that we have the TinyGo drivers repository. That's where we have all the different drivers that support sensors and displays, and additionally to that, supporting SD cards. So in order to communicate with an SD card, it's actually a SPI device, a SPI, Serial Peripheral Interface. And that is because we need to do very high-speed communication with this device in order to read and write files. So all it's doing, though, is just reading and writing bytes from a SPI interface. It doesn't know anything about what are those bytes consisting of. What are they? Just ones and zeros? No, it's an actual file system. So a file system is an organization of specific bytes into generally a couple of different sections, right? You'll have some type of section. We can even look at, let's actually look at this. FAT file system. Because we can probably see a diagram in Wikipedia that will illustrate my point. So back in the history, eventually no, I want a diagram. Let's go back to the pictures. That looks pretty good. Yeah, all right. So this is showing that we have some different sections of a disk which is formatted using the FAT file system, and it needs to keep track of where are the directories and where are the files in them, and then where are the actual data for all those files stored. And so you end up with usually a situation where you have different blocks of data on the disk or the SD card, and then you have separately a list of where all the files, their names, and then you might have more than one block, of course, as part of a file. And those blocks don't necessarily have to be in an order. Right? They could be in some random sequence, just if we opened a file, wrote some data to it, closed it, and then at some future time, opened that file again and added some data to it, it's very likely that we'll be occupying more than one block. So we have to have a list of all the blocks in order to retrieve this data. And on the disk, you end up with your partition, which is a section of the bytes which corresponds to what we would think of as a disk when we insert it, the root of that, and then all of the actual files and directories that are on that disk. So there's quite a lot to it. So luckily, we have another TinyGo project called TinyFS. And TinyFS is, as you might guess from the name, it is an implementation of file systems that are able to be used within TinyGo. And we actually have 2 different file systems currently supported. The first one is FAT, that we were just discussing, which is like the old school original. And then the other one is a file system called LittleFS. So LittleFS is a file system that is actually meant specifically for use on microcontrollers and other devices, which are very likely to have power failures and the other types of things that tend to impact small devices more than they do desktop computers. So it's very resilient for power loss. And then also, it's got something called dynamic wear leveling. So when you're reading and writing to something which is not a disk, which is actually a medium like an SD card or an SSD, solid state drive, if you just read and write data on the same section of the disk over and over, you'll wear it out. They only have so many reads and writes that are able to be supported by the actual physical atoms themselves. So LittleFS is a file system that's designed to accommodate that, but it's very inconvenient usually to use from normal desktop operating systems, so we'll just stick to FAT. All right, so what we need to do in order to make this work is, if we go over to the TinyGo drivers repository, or directory, I should say, we have, let's see, TinyGo. Well, actually, let's look at the program. Just a part of it, because it's actually a very long program. Excuse me. So, if we look under SD card, demos, it's in there somewhere, we'll see that we have a demo called TinyFS, which is using the SD card with TinyFS. And that demo is a console program that what it does is it actually launches a very simple console program that we can access from our serial port on our computer, and we can read and write data on the SD card on the connected microcontroller. Okay, what does that mean? So if we go and we take a look, we can see we have our microcontroller, and we will go and we will plug it in. We'll go and we'll plug it in to our Pi portal. And then we'll go and we'll flash the program. Let's make sure that we have the right versions. Yep, it's in there. Okay. So if we go TinyGo, flash, and our target is the Pi portal. And we're going to flash the examples, SD card, TinyFS. Then it will flash our program. And so now it should be running. And if we go over to a terminal, we launch the terminal, and we see that it says SPI configured reading flash info. Okay, so if I go and I say, actually, let's go help. No, there's no help. I thought there was help. Well, I thought, let's go and look and see what commands are supported. I thought it had help. Maybe that was the other example. Oh, here we go. All right, so we have a different list of commands that we can type in. And so I guess the first one is, this is the TinyFS directory, not the drivers. There we go. And the console, there we go. All right, here's the command supported by the drivers repositories example that supports TinyFS. And we can see that there's a few different commands: mount, unmount, format, don't want to do that. XSD, which is exporting the data for us to view. LS, we probably can guess what that does. Make directory, cat, write, remove. All right, let's see what happens if we type ls. Voila! These are the files on the SD card that is on the Pi portal. And I believe that it's a read-only file system, but let's see if we can make der testing. No, because it's currently configured read-only as opposed to read-write. So the reason for that is you might not want your microcontroller to be able to write data onto your medium if that medium contains something that needs to be kept secure. So, for example, if you have a digital certificate or something, and you want to be able to, when you're first setting up this device, you want to be able to put files onto it. But then once you deploy it, once you put it into the vehicle or the factory equipment or whatever, you don't want it to be able to write data on there because it could be used by an attacker to, replace the files on that. So one solution is to make it so that only when it's a special condition, like a special bootloader or over-the-air update, can we actually write the data, and the rest of the time we can only read it. So this is testing that particular capability. So we can't really do that much more, but we can use a few commands. We could say xxd 0512, which will display the first 512 bytes on the file system itself. And you can see that these bytes here don't have any real textual representation because they're the bytes that are normally used to indicate the beginning of a fat file system disk. So, but it's totally working. Great job, Sago35. So this is actually pretty exciting because there's a lot of things that we are going to want to be able to do, and we're going to need to be able to write files somewhere in order to transfer those files onto our device in order to execute whatever mysterious program we might be working on. Coming up in a future episode. Forgot to bring my bottle of water. All right. Very cool. Great work. So excited by that. Amazing contribution. I would like to see if it works with the flash drive. So in addition to the SD card, a lot of these devices also have flash memory, which is soldered directly to the board. For example, let's see if we can see it on GopherBot. I don't know if you can see it. So there's where is it? I believe it's this chip. This little tiny chip right here. Whoop. Hello. There we go. So this little tiny chip right there is I think 1 megabyte flash drive that is normally just empty, kept only for updating the bootloader generally, but we can read and write data from that once we have support for reading and writing data from our USB using the mass storage device interface. So we don't actually have that working yet, but once we do, we can do it now without TinyGo. We could do it by loading CircuitPython onto the board and then copying the files. And in fact, this is instructions that are on, we can flash it with CircuitPython, copy the files onto the drive that will appear as a mass storage device, then flash it with TinyGo and read it. But it'd be much better if we could just have support for the mass storage device. So that is coming, and I expect it will be very soon that we're able to do that, because that's actually some work that contributor Andrew Ardnew is working on to add more USB protocols, higher protocols like the Human Interface Device, HID, or the Mass Storage Device, MSD. So that work is underway, and I'm really excited about when it can land. So also last week, let's just shift over. Last week I started working on the Raspberry Pi RP2040. Let's see if I can find the window with... No, I'll just open it here. So last week I started working on the Raspberry Pi 2040 microcontroller, which is a really cool little microcontroller. Oh, gracias. Oh, I need water. So the Raspberry Pi 2040 microcontroller is the latest board from Raspberry Pi, and everyone's been talking about it, getting very excited about it. The support for this just landed in TinyGo, I think like maybe a couple of weeks ago. Several people had been working on it, and we finally got it there. So last week, I started working on adding the capability to have general purpose I/O input, and it did get merged. No, sorry, that's a different... That was due to a mistake I made. Here we go. Here's my pull request, which actually was just merged, which added... I started working on it, and I almost got it done. So it adds the ability to do a get, not just a set. So we can blink an LED on and off, or we can push the button and turn it on and off. So we can actually look at that if we want to. If we go over to, that's now in the TinyGo dev branch that I just built. This is the pull request here with the code changes that I had made. The only thing is we have to change the pins because the pin numbering, we don't have a standard pin that's got a name that's oh so convenient like button or LED, just because there's no built-in button. So if we go over to our button example, and I had cheated a little bit. I had changed the pins already so that the LED will use GP28 and then the button will use GP27. And then, similar to many of the other programs we've ever seen, we configure the LED as an output. We'll configure the button as an input. And then if the button is pushed, we'll turn on. Otherwise, if it's let go, we'll turn off the LED. So we do have to make sure that we are plugged into the correct pins. And I accidentally unplugged some pins. So let's go take a look at our pinout, RP2040 pinout. And we can take a look and see. I think I just plugged it into the pin right next to it. Usually that's what I try to do, just to make it a little easier. I have we can see this on the micro. I left the button plugged in. So the LED probably goes in not one, but 2 pins up. The Raspberry Pi, they do something nice, which is, you can see this on the diagram. They decided to make it a little easier for all of us who, are not able to see all that well. And you can see that the pins themselves, wait, where was that nice color? Here we go. You can see that the pins themselves will skip. So GP28, then it has a ground, then 27. So it's a little easier to not accidentally plug into the wrong pin. So the one we wanted was GP27, which is the, let's go look and see. 27 is the button, so 28, which is the pin right, is it above or below? Skipping a ground and then above it. So it skips up one. So if we go and we plug in my LED that I brought just for this exact purpose. So we'll plug in the red to the power and the black to the ground. And then we'll plug the yellow pin, which is the control pin, so that it's not directly above the other one, but it skips one, which should be pin 28, which matches the GPIO output pin that we've designated. All right, so now if I plug in my cable, we could focus a little, plug in my cable, and then go back to Linux so we can flash this thing. And if you remember last time, it was very funny watching me struggle to try to flash this board when I kept trying to double tap the button, and that actually doesn't do anything. You have to plug in the board while the button is held down in order to kick into the bootloader mode. So I'll plug it in, release the button, and it pops up with the bootloader drive. So I should be able to now say TinyGo flash, target, Pico. Pico? Is that the name of it? Board Pico. Yes, okay, Pico. Target Pico. And then it's examples. And then it is called button. Okay, so now it should have flashed it. And if we go over to, so now if I press the button, the LED should come on. Yep. Pushing it. So, okay, GPIO in and out. That's a good start. So, yeah, we really need that because we need inputs and outputs. Now, I thought, because I am not learned my lesson yet, I thought, okay, let's try again to add an entire new block of capability to the Raspberry Pi RP2040, all in just a few minutes remaining. We could do it. So I'm going to do git checkout -B for branch, and let's call it RP2040 ADC. See if you can guess which interface I would like to add today. Yes, you are correct. It is the analog to digital converter. Because I thought like it was a theme. You know, we just turned the dial earlier. Also, I know there's a rotary dial here somewhere. If nothing else, I can borrow Lorenzo's, so that'll work. I have another one somewhere. I just have to find it. He's already looking for it. He's like, yeah, I'll find it first. That's very true. But then you'll unplug it and you won't be able to plug it in again.
Yeah.
No, I'm kidding. All right, so let's take a look and see what it is we think we want to do, what actually is necessary. We can find it in here somewhere, the data sheet. There we go. All right, so what are we trying to do is we are looking at the analog to digital interface, which is one of the blocks on the RP2040. And so the analog to digital interface, here's a picture of it, shows you that it's got several different analog inputs, which all go through this same ADC, analog to digital converter. So kind of like we learned previously, there's a lot of pins on the RP2040. And so as a result, it has a lot of flexibility. So when we configure the ADC, normally what we have to do, and we can sort of take a look at this in the Pico SDK example. So normally what we would need to do is we would need to initialize the analog to digital converter just on the block on the chip itself. And then, which we do in TinyGo by using the init ADC function. And so the board that we were using before, the Arduino Nano 33 IoT, is a board of the processor kind, the AT-SAM D21, which is a microcontroller made by Microchip, which bought the company Atmel, which was originally making this chip. So when we are going to initialize this ADC, right, first thing we have to do is implement init ADC for the machine in question. So let's add init ADC to the machine package for the RP2040. Now, we do not have a separate file called machine underscore RP2040 underscore GPIO. The question is, do we want to add that to the GPIO, or do we want to put it into a separate file? So because the Raspberry Pi's machine packages are all pretty well organized by what type they are, I have a feeling that adding a new file will probably be our best bet. So let's add a new file, and we're going to call it machine underscore RP2040 underscore ADC.go. That way it matches the format for the other files and we can find it. And then we need to add an init ADC function to that. Of course, we also need to add the name of the package, which should be machine. But we need to add this build tag so that it only builds it for the Raspberry Pi, the RP2040, and not just for any of the other machines, because that, of course, would be a conflict since we already have init ADC functions for some of those. All right. So now, what should this init ADC function actually do is what we were looking at a moment ago in this datasheet and also in the Pico SDK. And we can see that the first thing we want to do is reset the block, which is just essentially turning on the overall capability of the processor. So I don't know what that does, but I guess we'll find out. And then we'll turn it back on by turning on the ADC registers CS, or ADC block CS register, to enable it. Okay, that sounds interesting. Let's go and see if we can find this ADC CS enable bits in our files, which are generated by TinyGo when we run our generator from the SVD files, which define the architecture for each one of these chips. It goes and it generates in our device package the wrappers that we use for all of the different processors. And so in the RP package, we have the RP2040, and this is one of the many files that's generated by that generator. In this one here, we can see that there is an ADC type, and it's got a CS register. And so ADC type, if we go and we just look at that, we'll see that there's only a single ADC interface exposed. So if we say just machine.adc, then we'll be able to access the registers under it. So let's go over to our, this is where I guess if I was using Golang, then the auto-completion would be pretty handy, right? So we'll try that next week if I don't get it done. So we would say machine.adc.cs, right? And then what are we going to do to that CS? Let's go back and look at the example. So we want to set the ADC CS enable bit on. So in TinyGo, we would normally just use the set command, because since the register is a volatile type, it's a special kind of memory, which is not just free memory for us to do whatever we want. It's memory that maps directly to the register that controls these capabilities on the processor. So we have to treat it a little differently. So when we set it, what are we going to set it to? Well, we want to set it to the value for the ADC type. And luckily, they're all listed for us as bit types underneath are the generated files. So if we look just for ADC underscore, these are the clocks, ADC type. This is for turning the clock on that controls the ADC. Somewhere down here, we'll hit the, here we go. So here are the bit fields for the ADC for controlling it. So now this is generated from that long XML file that consisted of all the different possible settings, and we can see that what we want to do is enable it, right? So it's this ADC underscore CS underscore enable, and if we just set this bit on by going back to our code that we were adding, and if we just set it to machine.thatBit, right, that should enable it. Let's go take a look at our C example. So it's ADC CS enable. That's what we just ADC CS enable, and we want to set, not just, we know that because we're using just the assignment operator here, equals. In other words, we don't care about the other register bits for the CS register. We can just ignore all of them, basically turn them all off, and only turn this one on. Okay, so that's what we did. And then, because it takes a little bit of time, in the datasheet it actually tells us this, right? That once the ADC block is provided with a clock, and its reset has been removed, writing a 1 to cs.en for enable, which is what we're just doing with that little bit of code, will start a short internal power-up sequence for the ADC's analog hardware. You notice that they have analog spelled with an E at the end. They're Brits, you know. So after a few clock cycles, CS ready will go high, indicating that the ADC is ready for business. No, it's ready to start its first conversion. I guess it would be an American manual if it said it was ready for business. All right. Enough of those jokes. Let's go back to the code. So that means what we want to do here is actually very similar to what we did in the machine package here. We have some code, or the machine package, sorry, for the ATSAM D21. And this wait ADC sync actually shows you a good example. So it's a for loop that's going to loop forever. And we don't want to say SAM. Actually, sorry. This should not be machine ADC CS. I think this should be RP2040. Let me just look at the GPIO. RP. Because we need to say import device RP. That way we're using the correct reference. So where's there we go. All right. So this should be RP. And this should also be RP. So we're setting the Raspberry Pi's ADC CS register to this bit. And then here we want to say RP ADC, and then what's the name of the register? It is also the CS register. And we want to say which bits is it that we care about. It is the ADC CS ready bits. So if we go and we look, probably very close to where we just were, we'll see that ADC CS ready. So we can check to see if this bit is set. That's the one we care about. It's actually RP. So we want to wait for it to be set. So we want to say if it's not has bits. In other words, if this bit is not yet set, keep looping. And then once it is set, it exits this loop, and we're done initializing the ADC, I believe. Let's go look. That's all that the ADC init does in the Pico SDK. Other than resetting this block, which let's just ignore that for now. Let's assume that when we first power up that the block is probably okay. So, whoops. So I'm going to say to do make sure block is initialized. Just to be sure. All right. So that should init the ADC. All right, so what else do we have to do to actually read it? Well, if we take a look at the Pico SDK, we can see in the include file it actually has the inline definitions of these functions. So in C, we can define functions in our .c file, but we can also define inline functions in our .h file, and it will basically take those and output the data directly for those wherever they're used. So it uses up more space as far as the program, but it's a lot faster. So let's go take a look and see. So GPIO init is, if we're going to init a specific pin, right, just one pin. So yeah, we know we're going to need to do that, right? And that's similar to what we were doing in the configure function, right? And if you remember, we did the same thing in the configure function that we used in our example that we were looking at with Lorenzo. So we're going to need to configure. So let's go back over to our Raspberry Pi ADC. So we know we're going to need to be able to configure an ADC to be able to be used. What else is it that we need to do? Let's go take a look and see what other functions. Well, init, we're going to need. Configure, we're going to need. Oh yeah, we need to actually get a value, right? So let's go and get. So we're going to define get. And right now, let's just say return 0. Because we can't have a function that doesn't have a return value if it says that it's going to return something. This way, it doesn't work, but it does return something. All right. So this won't actually do anything, but we can test to see, hopefully, if it even compiles, right? The way we can do that relatively easy is just by trying to compile the program that we were trying to use a minute ago. And if there's any syntax errors in that particular file, it won't even compile. All right, so it compiled, but it couldn't flash. So that's a good sign. We're getting somewhere. So let's go back to our code that we're adding. All right, so to actually configure, what do we need to do? Well, we're going to need to set it to a null function. So the GPIO on the Raspberry Pi, or actually the pins, I should say, are very multi-purpose. And we can set the peripheral I/O to support many different functions. We have a list of those in our implementation for GPIO itself, right? And if you remember, we had a list of those functions here under the GPIO function selectors that we can turn on. We can make it a JTAG for debugging, SPI for, once we have the SD card thing working. So the one that we're supposed to use in the case where the pin is going to be used for analog is we want to use null, right? Because null means don't use any of the normal GPIO functions. In other words, only use the ADC block to communicate. That way you don't end up with a conflict where the analog to digital converter is trying to do a read at the same time that the GPIO is trying to do a write on the same pin. That won't function, or that won't work, but it will function. Like it'll compile and it'll do something, it just won't do what you want, right? So let's go back here, and we want to be able to call the, and how did we actually do that? I believe that if we went and looked at our configure for the GPIO pins, we can see that it calls this init function, and then it sets the output mode. So we actually want to do pretty much the same thing, right? I mean, even though an ADC is it still a pin? Yeah, it could be a pin. It could be treated like a pin. So if we want to, but we don't usually do that, right? If we go and we take a look and see what does ADC config do for the ATSAM D21, you'll see that most of the work that it does is setting all these other special registers until, oh wait, it can treat it as a pin. It can just say a.pen.configure. So that means we can use this same technique, right, if we want to do a configuration. Because the first thing we want to do is say a.pen.configure, and we want to set the pin config to pin analog. Cool. But we have to implement that, right? Like there is no pin type yet for analog, so let's define one. Pin analog. So we'll add that to our spelling. So we'll add that to our list of pin modes. So now that's one of the supported pin modes. So now we still have to do something with that pin mode, right? In other words, if our case, when we're doing configure, is pin analog, what should we do? Well, I don't know. Let's go take a look. Well, first of all, if we go and we look at that init function, where's init? So init will set that function to SIO function. And now we don't want that here. What we actually want is to set it to this null function. So init is not doing exactly what we want, although it does part of what we want, right? Maybe the solution here is that we want to specify what type of init we want to do based on, or another option is just to init it twice, right? To call that, to first set it to the SIO function, and then to once again clear it. That's a little messy. That's not exactly how I would prefer to do it. But we're already calling init here. And if we don't want to duplicate our code, then, but I mean, one option is we can call this set function first. And we can repeat that for each of them. I think that's going to be the easiest right now. So if I take that and all of the pins, other than the analog, we're going to set to the function SIO. The analog, though, we're going to set to function null. I think it's null. Yeah. So this is going to just, this removes that one line from init. The last line, the one that actually sets it to which function, so this probably is okay. But there are a couple other things we need to do besides that, right? We need to disable the pull-down resistors and then make sure that it's not being used for normal GPIO input. We can't read a GPIO on or off and have the analog to digital converter read an analog voltage at the same time on the same pin. So let's first go and disable the pills. So we already have a function to do that, it turns out, that we are using, where? Configure. And, here we go. So we don't want to pull down or a pull up. So I guess we want to say, we want to clear the bits for both. So it neither says, we don't have a function yet for that. We have a pull up function, which turns on the pull up enable and turns off the pull down enable. So turns out you can actually turn on pull up and pull down at the same time, which may or may not have the side effects that you expect. So we have pull down, which, and I guess we should say pull off. And so if we say pull off, that should sound like it's a guitar thing. And we want to clear the bits for both of these. We want to turn the pull down enable off and the pull up enable off. So let's go here. And so after we set to a null function, then we want to call pull off. So we're neither up nor down. And then what was the last thing? Yes, we have to disable input. So now we do not actually have to disable input as much as we do. Well, actually, we kind of do. But I think we do that when we set function. Let's set input enable, clear output disable. So that's not good. That's actually not what we want at all. In fact, that set function is going to have an unintended side effect, it looks like, of turning input enable on, which is not what we want at all, right? We want to say that we want to do basically clear bits, that's a typo, of input enable. Whoop. So let's take this clear bits line to use as our starting point. So after we've done the pull off, then we want to clear bits of the input enable bit. This will make sense in a minute, I believe. All right, so we're setting to the null function. We're turning off both the pull-ups and the pull-downs, and we're turning off input enable. And that are all the three things that the GPIO, ADC GPIO NIT does. Looks like we're really close to being there, right? Because this should get everything ready. So now we have to just do an input select and then get the selected input. Okay. So input select is a matter of setting that CS register that we used before and turning on the bits that correspond to which input. So if we go and we look at that CS register, which we should see here in the data sheet under CS, and we can see that what's in that register? Here's the enable bit we used to turn it on. Then we have start once versus start many conversions. And then, that's not what I expect. That's not quite what I was thinking we needed to do. What I think we needed to do was just this read, actually. Just do a single conversion. Yeah, I think that's all we actually need to do. Because what that should do is that should turn on the read once for that. So you can have your analog to digital converter read over and over, just continuously reading, and then find out what the latest value is or you can just say, read right now and tell me the value. The reason why you would do continuous conversion is it takes some time to start the conversion process. And if you're really time dependent, you want to move really fast, you want to read really, really quickly, it's better to just be continuously reading and just get the latest value whenever you have time to check it. But in our case, we should be able to just use the normal ADC read just by saying read only once, and then once it's ready, get the value. It's not the most efficient if we're going to read multiple ADCs, but it should work for this initial implementation. All right, so let's go back to our ADC. So our configure, we went and we added to the pin configuration for GPIO so that we are doing all of our analog pin configuration here, which is setting to null, turning off the pull-ups and downs, and then clearing the digital input. And then we should be able to go and implement our last function, which is our get. And we said to do that, first we need to do is we want to turn on one of the CS bits for a single shot reading. And that was the one that was called start once. So we're going to start a single reading. Okay. And then we have to wait for it to actually get the data. Right? That's what was happening in this loop where we're checking to see, is it ready? That sounds really familiar. That's almost exactly like this loop we had right here, in fact. Ooh. That is the same exact function. Maybe we can make that into a helper. Let's call it func. And we need to make it off of our ADC. And let's call it wait for ready. And all it's going to do is not return until it's ready. And so we should be able to use that function here. Actually, we don't even need to make it, well, we don't need to make it a member function of ADC. We can just say wait for ready because it's always going to wait for ready regardless. Same thing here. So wait for ready. And then the last thing is to try to actually get the value, which should be in the result register. So if we go rp.adc, there should be result. Let's go and look at our definition. For ADC type, and yes, there is a result register. It's a 32-bit register. So it turns out that ADC values on the Raspberry Pi 2040 can be 32 bits, not just 16 bits. So we'll have to deal with that in a minute. But we should be able to just return get. The reason we have to say get is, remember, it's a volatile. We can't just assign volatile registers. We need to be able to use our functions to ensure the safety of those registers. And so when we do that, we use some functions in a package that's called volatile, that's part of TinyGo, that we use to protect it. So now this won't work correctly because this is a 32-bit value. So one way to address that is just to scale it down by half, right? In other words, we remove the number of significant digits. That's one way to do it. So we could just say, if we scale it over, by 16 bits, then we have to cast it to the right type, which would be uint 16, because it's actually not unit 16. That sounds interesting. So that should scale down the value from the max to the 16 bits that we actually allow. And then, that's a lot of bits to lose. I wonder if there's a way to set the number of bits to be used for the ADC conversion. I think for right now, instead of scaling it, let's just chop off the top. No, let's scale it. That seems better. All right, let's see if the code still compiles. We're almost out of time again, but we're really close to having something, I think. Okay, so it compiles. It doesn't actually work. So it turns out that there's actually an ADC example, but we're going to have to modify that a little bit for one of the ADC pins. So close. Let's see if we can actually maybe get this to work. So this example, it's plugged into an LED, and so if we turn up the rotary dial above more or less halfway, then it should turn on. Otherwise, it should be off. And so we need to use one of the ADC ports. So if we go and we look at our pinout, let's see which one we could use ADC 0, which is where GP26 is. So it's one right below the other two pins we have plugged in. So let's see if we can do this. Almost there. Plug in the power and the ground. Power red, ground black. And then we plug yellow into the pin right below the other pin, which was GP27. So GP26, which should be ADC 0. So it should be this pin right here. Okay. And let's turn it all the way down. And it should work with the built-in LED with the way that it's currently coded. But there is no built-in LED, so let's just make it GP28. That way, there is a built-in LED, but let's just make sure we're using the same LED. All right. Oh, wait, it's GP26. Yep, GP26. All right. Let's see what happens. We should be able to compile ADC. And it looks like it's going to compile. Okay, so let's unplug it. Press down the power button. What happened there? Unplug the power button. It pops up. Let's flash it. It flashed. And let's see if it worked. If I turn up the volume all the way, it seems like nothing happened. Wait. No. No, I don't think so. All right, well, we don't quite have it, but we're getting very close. We are, in fact, out of time for our little extravaganza today. So I wanted to actually do this to GopherBot, but GopherBot said no. Don't use me for your crazy experiments, Deadprogram. Like, you are one of my crazy experiments, GopherBot. So on that, I wish you a pleasant weekend, great hacking with you, and we will see you next time for more fun and excitement here at La People Live with Deadprogram. Sayonara.
Computer distant, computer doctor, everybody the guitars get flatter. Computer distant, computer never when you put it all on, put it all the computer distant, computer doctor, everybody the guitars get flatter. Computer distant, computer never when you put it all on, put it all the computer distant, computer doctor, everybody the guitars get flatter. Computer distant, computer never when you put it all on.